Thank you very much. I'm really happy to be here and to have the chance to give some mathematical clues about what you saw on Tuesday with those fascinating movies of collective motion. So if you remember the ships of Tuesday, you might be a little bit disappointed because these are not ships. These are bacteria. You saw them actually as well. But the point is that it might look like quite similar. And I think this was one of Tam's points on Tuesday to say that, okay, collective behavior can be handled at various scales, mathematically speaking. And I would say it's our goal to understand those behaviors. So these are those myxobacteria you learned about on Tuesday, and you see they essentially make no wave. They move around. They make little swarms. Some of them are isolated. You can see few of them which are moving around solely. So sometimes you will see the reversion. You will see some of them. If you catch one of them and try to follow, you will see them reversed after some time. And I should also say that the person who took this picture is in the room. Is Jean-Baptiste Saunier, third row, right there. And so you may ask directly. You may ask him questions about many things about those movies. So this is one glimpse of collective motion. You see them reverse. The way they do is very well understood at a single unit. There are motors inside. There is a moving machinery. But the question is, if you you have let's say individual rules, and if you sum up these rules, how do you get a picture like this one? And maybe more interestingly, how do you get picture like this one? So this one you saw them on Tuesday. So it's the same colony. It is taken at a much wider scale, and you see very remarkably on the left side you have those what is called rippling wave, which seems to be a key determinant in the developmental process of this bacteria, which is a social bacteria. And you see very clearly by eyes those. So if you zoom in this area, you will see pretty much the same as what was on the previous picture. But if you look into this area, you will see very coordinated and synchronized motion. And it seems to be still a mystery how bacteria make a transition from essentially this kind of stage to this one. There is a border here on time explained. This is due to the fact that there used to be a prey here which has been fully digested. And but from the mathematical side, you will essentially forget about the context and try to understand how, from simple rules, you can make collective behavior. So the sad part is that I won't be able to explain that. The reason is that the project is still ongoing, and it's not completely clear what are the correct biological hypotheses. We are still working on that. But I'll try to start from this example to motivate the rest of the lecture. And I will also present you other case studies for which we have a better understanding of the wave phenomenon. And more than that, this wave is a little bit more complicated than the wave which are usually, for instance, studied in reaction diffusion, where you have really a propagation, like an invading species. Here, the wave is really an accordion wave. You have at least two speed of propagation, one with a plus sign and one with a minus sign, like in the classical physical wave equation. So and these two are superposed and they interact with each other. So it seems to be a much more complicated problem, mathematically speaking, than only looking at waves. So let me show you another case study that will be studied later on, but which is somehow simpler and for which the mathematical understanding is more. Okay, so this will be my last movie before I'm going to the last but one movie before I'm going to the blackboard. So here is another group of cells. So different type of cells. These are eukaryotic cells, amoeba called dicty, which you might have heard about. It's like the superstar of mathematical biology. from back to the 70s. But this experiment is quite original because it's not the classical aggregation experiment of Dicty. It's a confinement experiment, actually. Sorry about that. Bad memories, but it's a confinement. So those cells are under a plate, a cover glass, transparent to take pictures, movies. And but I will detail the experiment later on. Let me just show you what happens to those cells in this experimental condition. So initially there is a droplet, so they are inside. There is no particular aggregation, and after some time, you see that you have a ring, a very stable ring, which emerges from this colony and which is moving outward. So you see it clearly here. So you have this ring. So this is, if you look into a cross-section, you have a wave which propagates at a constant speed with essentially a constant profile, and which is much easier to understand mathematically because now there is it's a one speed and there is no interaction. The wave is expanding and that's it. Still, it's not completely obvious to understand that. And sorry? Oxygen. They are lacking oxygen. So I will just in the experiment in a few words. There is a droplet of cells. You put a cover glass on top of them. So there is very quickly the oxygen becomes limited in the center because it can only diffuse from the side of the experiment, which is actually much. The cover glass is really big, so it's really oxygen. Sorry. Time t was 0. You put the glass, you wait, and after some time, oxygen is lacking because they consume oxygen at a very quick rate, and then they will essentially move outwards to find oxygen. Okay. They are desperate of finding oxygen. On those which are at the middle, they are stuck there. There is essentially no oxygen available, and they will move around finding something which they will not find. And just to show you what is fascinating also on this experiment, you can really observe this. You have the ring there. It's a very short time movie anyway. You have the ring there, and you can really follow cells individually. So you can really understand the individual rules by looking at those movies, by doing tracking of cells, looking at the statistics of the trajectories. You have really a massive amount of information that from which you want to extract something to understand the macroscopic behavior. So this is essentially my goal in this 3 lectures of today. Sorry, I will put names. So this is from Lyon, colleagues in Lyon, actually just in front of the Institut Camille Jordan. But the original idea from the CRCL, the Research Cancer Center in Lyon. The reason is that, so these are not cancer cells, but it was initially done 4 years ago, exactly the same experiment with cancer cell. And there is one good reason for that, is that it's very, very complicated to perform an experiment at very low level of oxygen, because oxygen is diffusing so fast that it's very complicated to you can do in a microfluidic chamber, but you have to put azote at a very high flux if you want to maintain oxygen at a very low concentration. And the reason to do that is that people believe that in tissues, in particular in tumor growth, but not only tumor growth, in developmental, in some developmental stage in tissues, oxygen might be getting down very quickly because of a local increase of cell population. And they want to understand behavior of cells under those conditions. And they found this clever way just to put a cover glass. It's seems to be a very low-tech experiment. You put a cover glass and cells are consuming oxygen. And now if you look at the ones which are trapped inside, which are not the one I'm interested in because I'm interested in the propagation, but if you look at the ones which are trapped inside, they are experiencing a very low, and they measured it. It was a tour de force to measure the oxygen concentration in this experiment during the course of the experiment, and they measured, it was below 1% of concentration, and even much below, they were reaching the limit of their, so it is very, very low concentration. Okay, so now let me move to the blackboard, and I will start with very basic mathematics to address some questions which are raised by the first case study, which are the rippling waves. Which are done by those myxobacteria. So Myxococcus is the name of the species, and this is an ongoing work. With Tam Mignot, that you saw on Tuesday. And, as I said, Jean-Baptiste Saunier with here. And so it's really a fascinating problem, and it has been studied in math biology for quite a long time. And for the biological question, it dates back to the 90s and 2000s by a group of Welsh and Kaiser that observed those waves and addressed the questions on why is it so. And then there have been some modeling work in the 2000 by a group of Higoshin, those two people, and George Oster, who developed models and the idea that waves are interacting with each other when they are moving in opposite direction. And then there have been a lot of works by this group and by other mathematicians like Fritjof Lotzer, Angela Stevens. There is one paper in O2, and there have been many contributions actually by Angela Stevens. I remember from from old times where she was presenting these models, and there are certainly many other contributions. Actually, I'm not completely aware of all the literature, but I like to highlight one very interesting paper by Angela Manhart, which follows a series of papers with Pierre Degon on U, where she presented a model that we were very comfortable with, and also Laura Kantler PhD thesis, is also on this subject, and there is also a very nice paper with Sabine Hintmeyer, Angelika Manhart, Laura, and Christian Schmeiser, and modeling the interaction between individuals. So there is a lot of literature and a lot of other studies on more generally hyperbolic model where you have a persistent motion. So the key word here for me is persistent motion. You see that in those movies of flipping wave, for me maybe the first striking observation, is that diffusion is clearly not the right way to describe motion. Usually, when you are looking at waves, let's say in reaction diffusion equation, you are looking at you are assuming that there is a diffusion of individuals. It's clearly not the case. This synchronized motion is very persistent, and to me it happens at such scale that you cannot make a diffusion limit. You really have to look at cells moving in one direction, cells moving in the other direction, and somehow you cannot average those. So this will be the starting point of this lecture, which is persistent motion. It will be. It might happen. It might look very basic to some of you, but I like it's a good introduction to the problem, and it's the idea that you have myxos. Let me draw myxos moving on one side, and then it might be the same after reversion. You have cell moving on the other side, and this will be V. This plus V. Minus V, and I will call V equals to 1, just to put units. So the idea that it's very, if you look at them, at those waves, it's very natural, as a very basic first step, to split the population into two subpopulations, the one which are moving to the right and the one which are moving to the right. So let me give name to that. So I will, ft of x will be the density of the moving right cells, and G so then you can start writing a model which might look like, and this was a usual model by Lutcher and Stevens. So you have just transport at speed 1 for the cells moving to the right. Just by definition, you have a plus 1. You have the transport speed here, the v, which is 1. And then they will essentially change direction. And then you have the same for the right moving particle, the left moving particle, except that there is a -1 here, because they are moving at speed -1. And then you have some rate of exchange between the subpopulation, between the two subpopulations, when they essentially, in the picture, when the waves interact, they exchange individuals. And if you look at the very first paper, what you find is that there is a rate of change. So you lose cells that are moving to the right, but go into the compartment where they are moving to the left. You have the loss term and the gain term, they are the same, it's just a transition. And then vice versa, you have those which are moving to the right. C'est un G, sorry. So the last one is not correct. And then the question is, how is this interaction? So if you have a linear model, you will not find patterns and those ways. So you have to put some feedback, some nonlinearity. And the usual hypothesis that comes from the very early paper by Welch and Kaiser is to say that those ways which are moving to the right are sensitive to those cells which are moving to the right are sensitive to the cells which are moving to the left by some sort of putative cell contact signaling. So they would express some signal at the head, both of them, and when they enter into contact, they will essentially reverse. Reverse here, if you remember, they just change their motor system direction, and they are without turning, they just change their speed. So if you put that into the equation, this is what you get. You have a J here. Those cells which are moving to the right are sensitive to the cells which are moving to the right with some density-dependent function. And you do the same here, because it must be the same. So this is a very strong hypothesis, which is sensitivity it's a density dependence, reversal rate, the rate of reversion to the opposite direction, to the opposite cells. Okay, so this is one hypothesis, and if you look at that, actually it does the job pretty well. Let me just show you in a few. You can do what was done initially is to do a linear stability analysis for this problem. This is the first. This is the first way how to address patterns, is to do how to identify pattern. Here, patterns mean wave formation. The first step is to investigate linear stability of the spatial homogeneous. So you assume that f and j will be some constant, so it's a f of t of x, some constant value plus some small perturbation. So it's a small perturbation. You linearize your problem. Exactly as you would do for Turing instability analysis. And if you do so, it's an exercise that you can it's an exercise that you can do. The left-hand side, of course, of the system is linear. The right-hand side is non-linear, so you will find essentially mu times a small part plus mu prime of rho star times the small part. So how it looks like. So what you will find is dt f tilde plus dx f tilde, and there you will get, I took notes, you get minus mu prime of rho star, the value of the homogeneous, times rho star, because it's a f value, times g tilde, and you will get the same with the f, and then you will get the minus mu rho star f tilde plus mu rho star g tilde. Okay, and you have the on vice versa for the j. And so if you rewrite this, you will find. And if you take the Fourier transform and you look at the spectral problem, so look for, if you seek exponentially growing or decaying solutions in time. Because the problem is essentially invariant by translation, you can take Fourier transform in space. There you will look for the eigenvalue. You will find f hat plus e c f hat. And here we will get, if you combine everything together, it is mu prime rho star minus rho star, minus mu of rho star. And this is times g f minus j. If I'm correct with the sign. Should be that. And you have the same for j, of course, except that you have a minus here. And now, if you look at the sign of the eigenvalue of the real part of the eigenvalue is the same as the sign of this quantity, mu prime rho star minus mu of rho star. So this is a key quantity that will determine whether the homogeneous state is linearly unstable or not. And so it will be unstable if this quantity is positive. So you see immediately that it's you need a non-linearity on the mu, because if you take a linear function for mu, so suppose mu is a plus b rho, so suppose you have a linear response to the opposite direction, then what you will see is this quantity is simply b rho minus a plus b rho, which is minus a, which is negative, because of course you want this to be a positive rate of reversal. So in this case, there is linear stability, unconditional. So you need some nonlinear response, and essentially what you find in those papers typically is a sigmoidal response for the mu, which looks like this. So if you have a sigmoid for mu, it may happen that in some regions you have such an instability, and then you see patterns emerging. And if you run simulations, you see waves. If you look at Angelica Manard's paper, it is very well explained with more complicated models, with more stages, and with more complicated functions. And even the patterns are constructed, waves are constructed under some hypotheses, because as I said before, it's a complicated problem because you have waves moving at least in two directions and interacting. It's a very nonlinear problem. But in her paper, you will find, if you're interested, very, very insightful analysis about this problem of pattern formation. Are there any questions at this point? Okay, now the point is that, yes. So this one is a plus because so this one is a plus. It comes from the last term when you are looking at the perturbation of J in the linear part. This is the F, which is essential, which is the leading term. Here is the F. Okay, I should use a pointer. Okay, when you plug this into the second term, there is a plus here. So this has two contributions. One, which is essentially the leading part, which is a rho star, which is there, and the G tilde, which is a small perturbation. And the second contribution is written. Yeah, so this sign is not correct. This is what you were telling me. No, this one is correct. Comes from it. So this is the second contribution. This has two contributions. The two is a plus sign, which comes from there. I think signs are correct. Okay, now came our joint project with Jean-Baptiste and Tam. And Tam, after 20 years of research on rippling waves by several groups, and seemingly a recent interest from biologists, because those people were more biophysicists. Tam was telling us that this is a very, very questionable hypothesis. This signaling to the opposite, this cell-to-cell contact signal was hypothesized in the 90s, but people are still looking after it. There seems to be no clear such signal. And more than that, there are some mutants that were identified and were supporting that, but apparently what the genetic basis of those mutants seems to be very different from signaling and movement. It seems to be more a metabolic mutant. So it seems to be something which is at least not yet supported biologically. So then what you have to do is to question the model itself, of course, because this, as I told you, is very nice to produce waves, but there seems to be at least a question about the hypothesis. So then the natural way to do is to go to the movie and look, and then there is some kind of new hypothesis that emerge, which is much more basic, which is to say that when it's crowded, then the cell will have a tendency to reverse, just because you are moving at a constant speed with your motor machinery in one direction. And when you experience a crowd, you will, after some time, you will not be able to go further, and you will just change direction to keep moving. So those cells seem to keep moving, they never seem to stop. They are moving around all the time during this rippling phase. So what it does to the model? So you go back to your model. And you assume that they are sensitive not to the cells going in the opposite direction, but rather to the local density, which is a very crude assumption, which is also questionable, as all modeling assumption. But let's look at what it does to the analysis. So I will keep the same, and I will just change. Let me just go a little bit quickly, and assume that now the cells are sensitive to mu rho plus mu of rho j, and this is a mu of rho f and the minus mu of rho j, and okay, so now this, as I said, is a questionable hypothesis, so I replaced it by an alternative. I don't say it's wrong, it's just I replace it by a density-dependent, say local density dependent rate, which could be like a congestion signal. Due, as I said, maybe to some the machinery which is which cannot if you are stuck there, you change, you reverse. This is a hypothesis. So if you look at this model, I try to do quite quickly. You see that there is a main difference in this analysis. Here you add the two terms, the terms that gives a positive sign in this linear stability analysis comes from the mu prime and come from these terms and these terms. And essentially due to the fact that this j was the one which was inside the mu and this f was the one which was inside the mu. But now if they are the same, mu rho and mu rho, because of kind of a symmetry, in this case you see that both cells which are moving in the opposite direction feel essentially the same signal. Okay, this is what you say here. So if you do that, you have a minus something, plus something, and these two are the same because they experience the same signal. So they cancel each other, and it remains only the minus mu. So the minus mu is always negative, and it's always linearly stable. So this case is, you can do by a very simple exercise the same stability analysis. Two terms are cancelling, and you have a linear stability for any mu which is positive, which is a rate, it must be positive. Okay. So what's next? Seems to be hopeless at this point, and maybe this hypothesis is not only a biological quest, it's also a mathematical requirement. And the point is, and I think it was one of the starting point of this project, was an article that came out of Tam Mignot's group, and actually he presented on Tuesday. And just let me give you a very quick description, a recall of that, which is an article, biological article with some mathematical modeling. So I was not involved in that. I read it carefully, and it was explained to me, saying that first observation, there is a refractory period, but this was known for a very long time. During which, after reversal, in which cells cannot reverse. They have to wait some time. It was very well explained by Tam on Tuesday due to the molecular protein networks involved. It takes some time to essentially move all the molecular players from one end to another. But this was described for a very long time. This was known in the 90s, and it's not only for those type of bacteria. This type of behavior is also very well described in dicty. So you have many such waves have this idea of having a refractory period. But more than that, and this was the new result, is that it can be modulated by, let's say, signaling pathways. And then under some conditions, the cells are able to reduce this refractory period so that they are, in a sense, more sensitive or more quickly responding to the environment. Here, environment means for us the entire population which they are interacting with. So in terms of models, of course, it's a bit more challenging because there is one additional variable you have to take into account, not only the space and the direction, which is these two subpopulations, but you have also to follow the time between a reversion. Okay, so let's try to do that, and I will try to explain very quickly the framework, but it's always the same idea. You write a model at this point, and you make stability analysis. As I said, I will not be able to explain the wave for this case study. So I will have my new density with an additional structure. By the way, this is the reason why I was very interested into that project, in addition to the very exciting collaboration and the amazing problem and data that emerged from this collaboration, but also because there is some structure in the wave. All individuals are not the same. They are heterogeneous, of course, in space and in direction, but also in the time since the last reversion, and I'm very, very interested to this type of wave propagation with structure. In this case, we will have f, t, x, and we call it R because it's due to the Roma dynamics, which is one of these proteins, which we call it's Roma protein dynamics, that drives this refractory period. That it has to relocalize to one end, and then you will have essentially dxf plus drf. So this is motion. And this is aging, because times is flying, you know. So you have you are counting time since the last reversion by 1 unit of time at each step, and then this there is a constant that I will take a constant rate here, and here this is the heaviside function. No, it's R of rho times f. So what does this say? That you have a constant reversal rate after beyond R bigger than R. This is the heaviside function. 0, 1. Okay, so if your R is below this refractory period, so this is a refractory period, which is density dependent. If you are below, this is 0, so nothing happens. The cells are moving, keeps moving in the same direction with the same speed, and they are counting time since the last reversion. And when this time is beyond this refractory period, which is a parameter of the biochemical network, then it reverses with rate 1. You can always put, you can also put density dependence here, but for what I'm going to say, it's enough to have rate 1. Then you can, of course, mix both effects. So in a very, very short few minutes, you can do again linear stability analysis. For this problem. It's a bit more involved because you have the structure, you have to incorporate this. It's not now invariant by translation. I forgot to say, of course, sorry, that there is, you have to, some insertion I forgot. Of course, you have to take into account the reversal, where you reset the time between reversal. And this is just the integration of all reversion events of cells moving in the opposite direction. Which in this case is essentially, due to the form, it's only the sum of all the density that have gone beyond the refractory period. So you can do linear stability analysis. So this I will not give you any details, but it's the same idea. You linearize. You have to look at the spectrum of that. You take the Fourier transform of this. You cannot do much because it's not invariant by translation, but you can integrate explicitly because it's just a renewal equation. And you compute. It's not completely obvious, but you can compute. And at the end, you identify the complicated function that you can solve numerically. And you can plot the linear stability analysis. And you have essentially two parameters in this problem. You have as before, you had essentially two parameters, which are the mu and the mu prime. So it's the same function mu, but you see that it depends on this number. At a given density rho, it depends on the mu prime and the mu. And in some places, you may have a large mu prime because high slope, so you will have instability essentially in that region and stability there and there. So essentially two parameters, mu prime and mu, and here it's the same. You have essentially two parameters, r prime and r. And if you write r prime, so the correct thing is to try to have r prime of rho star times rho star, and here r of rho star, if I'm not confused. So you have a two-parameter plot. You can draw the linear stability. You can look into this, let's say, phase plane, parameter plane, and you will find that there is a transition between unstable and stable, which will look like this. So it will be unstable here, unstable there. And if you look at what was put into the model for the function r, so the equivalent of this type of function, what you will see is something that goes like this. And will converge to 1/2 actually, with this specific function. You have a limit to 1/2. Anyway, so what you will see is that if the refractory period of course you have to prescribe what is R. Here it's given as two independent parameters in your linear stability problem, but when you have a model, you will prescribe what is this density dependent dependence look like. So you have to prescribe some R. So this is, I should say, this is a modeling choice, but which emerged before doing the analysis, of course. And if you do that, you will see that if the refractory period is not too small, you will see instability. And the point is that it cannot be too large as well, because it's known that the refractory period has sort of a maximum. So depending on the parameters, you may have a range of refractory period corresponding to this piece of the function for which you will see instability. I should not draw there, but you will have instability here. Okay, and let me maybe to conclude this first. Let me just show you the movie that were partly displayed on Tuesday. It's just to go back to not directly to the experiment, but to something which looks like an experiment. So Jean-Baptiste did first a 1D density model, and then he turned it to so these are the real experiment. He turned it to a particle simulations, incorporating this refractory period, the counting time, and so on. And this is what he obtained with this density-dependent refractory period. Again, with two different conditions on the right and on the left side, where you see clearly these patterns emerging, and it seems to be a reasonably one-dimensional pattern if you look into one cross section. And as Tam showed, it has very comparable statistics with the experiments. And if you rely only on the density-dependent turning rate, so the mu of R, based on what I presented before, you essentially see no clear pattern emerging. So it seems that if you rely on a less transient assumption hypothesis, which is to say that it's only a local congestion that may drive the pattern, if you omit this result, this extremely nice result about this modulation, you see you don't see patterns. And if you incorporate this new biological insight, you see the emergence of patterns depending on the conditions. The conditions are not the same on the right and on the left. I think the density is not the same, and you see the emergence of patterns. So I think my time is over. Thank you, and I will resume more waves later. Thank you.